A non-conducting sphere, radius r0 and total charge q, has charge per unit volume ρr equal to ρ0 r over r0 cubed. Find the electric field inside and outside the sphere. So how will we go about doing this question? There's quite a lot of information. Firstly, we're using a sphere, so probably Gauss's law would work nicely. So let's just state Gauss's law here. Integral of the electric field vector dot producted with the surface normal vector is equal to the charge enclosed over epsilon naught. So because of the symmetry of the sphere, we decided to use Gauss's law. So if we draw the sphere with a radius of r0, then perhaps we can draw a Gaussian surface. Perhaps at some distance r, we can draw a spherical shell, a sphere there, and we can find the charge enclosed, and then because of the symmetry, we can see that if we look out, the electric field must be going out radially in all directions, and also the surface normal, we can see that that is also normal, that is also parallel to the electric field vectors. So that's really nice. So this side of the equation can be simplified. That's why Gauss's law works so well for symmetry. Yeah, that should work. But first of all, we have to find we have to find the charge enclosed in the sphere. So how would we find that? We know, just by definition, this is the charge per unit volume. So the charge per unit volume, ρr, is defined as the total charge over the total volume. Okay, cool. What about an infinitesimally small charge enclosed? Well, you can also rewrite this as dq over dv, an infinitesimally small charge over infinitesimally small volume. What does that even mean? I'll try and show that throughout this video. So then, what do we do now? We can rearrange this to get dq equals to ρr dv. And then now, it looks like an integral sort of thing. And if we find dv in terms of r, and we know ρr in terms of r, as stated in the question, then we can find the charge enclosed at some distance r away. So let's try that. And also one other thing to state is that we can find the electric field inside the sphere at some distance r, and also outside the sphere, perhaps a surface like this. So that they seem to be the two conditions we want to look at. So let's get into it. What is dv? If we consider let's now consider a spherical shell at some distance r away, any distance r, and at some distance r, we can consider a very thin spherical shell with thickness dr. And as this spherical shell gets thinner and thinner and tends to 0, we can use this notation dr. And that gives a really nice approximation that dv is the surface area of the shell, 4 pi r squared, multiplied by the thickness, analogous to, say, a rectangular sheet. So if we stretch this out, we might get a surface like this with thickness dr and surface area 4 pi r squared, and this is like an area. Perhaps I should draw it like this. And then the volume of this object would be 4 pi r squared times dr. So this is the infinitesimally small volume. Nice. So we know rho r to be this and dv to be this. Let's substitute those equations into here. So we result in dq equals rho naught r over r naught cubed times 4 pi r squared dr. And that is equal to, well, let's get the constants to the front. 4 pi rho naught over r naught cubed. That's using these variables. And now it's just the r cubes and dr. So what is r cubed times r squared? It's r to the power of 5 dr. Nice. So then we have to consider an infinite amount of these infinitely thin sheets. So what is this process? That's an integral. So let's integrate this. So that implies that the integral of dq, and what's the limit? So we start at 0 and we go all the way to this distance r, where the charge enclosed is just the charge enclosed. And that is equal to, let's keep the constants out, 4 pi r naught over 4 pi rho naught over r naught cubed, integral of r to the power of 5 dr. Nice, that works perfectly. And that is from 0 to some distance r away. And let's call this a dummy variable r dash, because people like to do that, and there's reasons for that, which I still do not understand. Let's keep going. This gives charge enclosed equal to 4 pi r naught over r naught cubed, r to the power of 6 over 6, and that's evaluated between r and 0. Let's not forget the dummy variable r dash. And then that is just equal to 4 pi. I guess we can cancel the 4 and the 6, like so. 2 pi rho naught r to the 6 over 3 r naught to the power of 3. Perfect. So we know the charge enclosed at some distance r away. Now we can just apply Gauss's law, and the diagram's getting slightly messy, but we're considering some distance r away. What is the charge enclosed in here? And what is the electric field at this distance, at this radial distance, because radial means going out in all directions. Nice. So let's use Gauss's law, stated here. Let's rewrite it down here to get some space. Nice. So we know that the electric field is parallel to the surface normal at every point, as we are shown here. Say electric field here, the surface is here, tangential, and that the surface, the vector normal to the surface is also parallel to the electric field. So we know that the dot product, which is given by so E dot ds is the same as the magnitude of E, the magnitude of ds, times the cosine of theta. And since they're parallel, theta is 0, so cos 0 is 1. So it's just the magnitude, and I'll call it an E and ds. Nice. Nice symmetry there. So also let's consider another thing. At some distance r away, at some distance r, the electric fields, all of the electric fields, is constant at this given r because of the spacing between each of the arrows is equal, given that the spacing is at equal intervals of theta. But we don't have to get into too much detail there. So we want to say that the electric field is constant. The electric field magnitude, we could say, is constant at given r. Nice. So that means that this can be simplified to integral of E ds, and since E is constant at some distance r, some given distance r, then that implies that E, we can get the constant out, and we get E integral ds. Nice. So let's rewrite this as integral E integral ds equals Q enclosed, and this is this thing here, 2 pi rho naught r to the power 6 over 3 r naught cubed over epsilon naught. Don't forget that epsilon naught. I do that all the time. Nice. So this thing, what is the integral of all the surfaces on the surface? That's just the whole surface itself. So at some given r, the equation for the surface of the sphere is 4 pi r squared. So we can rewrite it as E 4 pi r squared equals 2 pi rho naught r to the power 6 over 3 r naught cubed epsilon naught. And let's cancel a few factors. Perfect. And let's cancel this 2. R squared, R6 cancel. And then we can rewrite this as rho naught r to the power 4 over 6, 3 times 2, r naught cubed epsilon naught. Perfect. And this is the case, this is the electric field where where r is less than the radius of the sphere, so it's within the sphere. What about when we are outside the sphere? Well, that would be this surface here. Say at some distance r away, we are outside the sphere. We form a sphere outside the sphere, Gaussian surface outside the non-conducting sphere, and that means that r is greater than r. What does that mean? To the charge enclosed. Well, the charge enclosed will be the whole total charge in it, and that would be when r is a distance of r away, big R away. So this can simplify to 2 pi rho naught big R to 6, big R naught to 6, my bad, R and R naught is the radius of the sphere, over 3 r naught to the power of 3. And we can cancel these out, and we get 2 pi rho naught r naught to the power of 3 over 3. Nice. And then we can apply Gauss's law. These points are still just as valid, and we can say that E times the surface, which is still 4 pi r squared, which is equal to the charge enclosed, 2 pi rho naught r naught cubed, over 3 over epsilon naught, and we can cancel some factors, and we get E equals rho naught r naught cubed over 3 times 2, 6 epsilon naught r squared. Nice. And that's for r is greater than r. So that's how to do the question.